Right now, someone is typing a simple domain name into their browser, and within milliseconds, a web page appears. It is served from a global infrastructure located in a data center they have never been to, using a technical address they have never memorized. Computers on the internet do not communicate using names. They require specific, numerical IP addresses to locate and route data. Humans, however, rely on semantic, memorable words. In the early days of connected computing, bridging this gap was entirely manual. A single text file called hosts.txt was maintained by a research center and physically distributed to every computer on the network. As the network grew in the early 1980s, updating a centralized file became physically impossible. Naming conflicts spiked as multiple machines claimed the same title, and the manual update process caused delays across the system. A monolithic, centrally maintained list cannot scale with a growing network. To survive, the internet required an architecture that distributed this data across many locations at once. In 1983, Paul Mockapetris designed the Domain Name System, or DNS, to solve this specific bottleneck. DNS is a globally distributed, hierarchical database. It translates human-readable names into machine-readable IP addresses by spreading the mapping data across thousands of servers worldwide. While DNS decentralized the physical infrastructure, its administration remained under the control of central entities. This created a tension between the efficiency of the network and the security of the naming records themselves. This trade-off, distributing the hardware while centralizing the authority, sets the stage for the specific vulnerabilities that decentralized naming systems are now being built to address. Organized as an inverted tree, no single DNS server holds every record. At the top is the root level, 13 logical starting points. Below are top-level domain servers, managing categories like .com. At the bottom are authoritative servers, holding the definitive IP records. By distributing authority across these three discrete tiers, the system removes central computational bottlenecks. This distribution allows the system to handle hundreds of millions of domains and billions of daily queries. We can see this architecture in action by tracing what happens when a user types youtube.com into a fresh browser session, initiating a cold DNS lookup. The request fails local memory, passing to a recursive DNS resolver. The resolver asks the root server, which refers it to the .com TLD, which then refers it to Google's authoritative server. The server returns youtube.com's numerical IP address. This multi-server global negotiation usually completes in under 100 milliseconds because each tier only provides a single-step referral to the next level down. If every single web request had to query the full hierarchy, the global root servers would be overwhelmed by the volume of traffic. To prevent this, DNS stores specific data types called resource records. An A record maps to a standard IPv4 address, while an AAAA record maps to the longer IPv6 format. Attached to every record is a time to live, or TTL, value. This number specifies exactly how many seconds local resolvers can cache the data before they must fetch a fresh copy from the source. This creates an operational trade-off. A short TTL allows for rapid updates if a server moves, but it increases network traffic and latency by forcing more frequent lookups. The system is designed to favor local memory over global computation. This aggressive edge caching is what allows the core infrastructure to support the entire web. The 1983 protocol was built for a cooperative research network where nodes trusted one another. Because of this, the original design lacks a way to verify that a response is actually coming from the correct server. Attackers exploit this by injecting false IP addresses into a resolver's cache. When a user attempts to visit their bank or email, they are redirected to a malicious server without ever knowing the address was tampered with. To defend against this, engineers developed DNS Security extensions, or DNSSEC. DNSEC uses digital signatures. By applying cryptographic keys to the records, resolvers can verify that the information received is authentic and has not been modified in transit. These signatures create a chain of trust. The root servers sign the records for the TLDs, and the TLDs sign the records for the authoritative servers, allowing the resolver to verify every step of the resolution. This method of using cryptographic signatures to prove the integrity of data is a core technical principle shared by blockchain networks to secure ledger entries and transactions. Despite their decentralized design, blockchain networks depend on traditional internet infrastructure to stay connected. When new Bitcoin or Ethereum nodes join the network, they often use DNS seeds, specific domain names that resolve to the IP addresses of active peers. Furthermore, the web interfaces for wallets, exchanges, and block explorers all use standard DNS to make their services findable by users. This creates a contradiction. Applications designed to be permissionless are still accessed through domain names managed by centralized registrars and government authorities. As long as central entities have the power to seize or redirect domain names, the interfaces to the blockchain remain subject to traditional administrative control. This diagram contrasts traditional DNS with the Ethereum Name Service, or ENS. ENS performs the same lookup function without relying on centralized servers. Instead of a registrar-controlled server, ENS uses immutable smart contracts on the blockchain to store and resolve names. Control of these names is governed by cryptographic private keys. This removes the administrative policy layer, ensuring that only the owner can modify the record. Decentralized naming also expands what a name can represent. ENS can resolve a domain to an IP address, but it can also point directly to a crypto wallet or a distributed file system hash. While 1983 DNS successfully mapped human intent to network locations at scale, ENS applies those same principles to the blockchain, allowing the mapping to exist without a central authority to manage it.